Good day, everyone. Welcome once more to today's class. So in today's class, we're going to be dealing with 50 high-yield questions you will see in a typical physics CBT exams. In the course of us attempting these questions, I want you to always pause the video, try to solve it yourself, and see how many you score out of 50. Let's go straight away to starting. All right, so the first question says that the electrostatic force between two charges obeys an inverse square law, meaning it varies as A says 1 over R, B says R square, and C says 1 over R square, and D says R. Choose an option. All right, let's go to attempting this. Force. Now, this particular question is gotten from what we refer to as Coulomb's law. And Coulomb's law mathematically is force is equals to the constant scale, all of the first charge, times the first charge times the second charge, all over the square of the distance between those charges. Now, if they are dealing with how the electrostatic force is actually relating with the inverse square law, what we refer to as the inverse square law is simply, we're going to say force is equal to 1 all over what the radius is in its squared form. This is what you refer to as what? The inverse square law. The inverse square law is simply 1 all over what? R squared. So it happens that the correct answer is option C. The second question says that a nucleus is represented as, we have this particular element is potassium, having a mass number of 40 and an atomic number of 19. And they're asking us that its number of neutron is, A says 21, B says 19, C 40, D says 59. Now, very importantly for you to know, that's what we refer to as the mass number of an element. The mass number, before I talk about the mass number of an element, let's assume that this is an element X. There is a symbol at the top of this element X that is written as A, and there's another symbol in this element X written as Z. Where this down alphabet, the Z, is referred to as the atomic number of this element X. All right? So Z is the atomic number. And then the symbol A is of this particular element X is what we refer to as the mass number. Now, the atomic number in itself is simply the total number of protons in the nucleus of an atom. And the mass number is simply the proton plus your neutron. Take cognizance of that. The mass number is what? The proton plus the neutron. Now, for me to get the mass number A, I must add my proton plus what? My neutron, to be able to get the mass number of an element, right? Now, since this proton is what Z is, because Z is simply the number of, or the atomic number Z is simply the number of protons. So I could say that this atomic number is Z plus my neutron. I will still be correct. So to find my neutron N, I'm going to say that the neutron N is equals to my atomic number minus, my mass number minus what? My atomic number. So anytime you are asked to look for the number of neutron in an element, the simple thing is you're simply going to do the mass number of that element minus what? The atomic number of that given element. And this element is potassium. So it happens that for us to get the total number of neutron N, we're going to say the mass number, which is what? 40, minus the atomic number, which is what? 19. And that will give us a total neutron of 21. So an element with a mass number of 40 and an atomic number of 19 will have a total number of neutron of what? 21 in it. So it happens that the correct answer is option A. The next question says that the unit of magnetic flux is the dash. A says Tesla, B says Henry, C says Ampere, and D says Weber. What do you think the answer will be? I believe you are attempting, and please do it to always drop your answer or in the comment section. All right, option C, we all know that Ampere is the measurement unit for current. Henry here is what you use in measuring inductance. Weber is used in measuring the magnetic field strength, or you call it magnetic flux density of a particular material medium. Tesla here is a correct answer for magnetic flux in terms of its units, right? So option A is correct. Don't forget, Henry is inductance, Weber is magnetic field strength, or you call it magnetic flux density, Ampere is to current, Tesla is to what? Magnetic flux. Question 4 says, a rod of proper length, 20 meter, moves at 0.6 the speed of light. I will give a Lorentz factor as 1.25. We're asked to find its measured length. The options are 25 meters, 16 meter, 20 meter, and 12 meter. I hope you're solving already. All right, for us to solve this question, there's actually a formula that relates our proper length to our contracted length and our Lorentz factor. That formula is our contracted length is equals to our proper length all over our Lorentz factor. Now, we all know that there's actually a longer formula that we can use in solving questions like this. We can say that our contracted length is equals to our proper length, then the square root of 1 minus the speed squared all over the speed of light squared. All right. But then we all know that we've actually been given our Lorentz factor already, and we have been given our proper length. So it's easier for us to find our measured length. As this measured length means the measurements of the person that is looking at the object as it's moving. All right. So the observer that observed that object as it's moving, the length with which he would describe that moving object is referred to as what? The measured length or the contracted length. Then the person that is in that vehicle that is moving, the measurement that person will give is what they call the proper length. All right. So since we already have our Lorentz factor, we can just go straight. So in a CBT question, once you're given your proper length and your Lorentz factor and you're asked to look for the contracted length, just apply this formula and you get the answer. So our proper length is equals to our contracted length all over our proper, this is our proper length all over our Lorentz factor of what? 1.25 meter. And if we do 20 divided by 1.225, it happens that we got an answer of, our answer is going to be 16 meters. Notice that the contracted length, as a person that is outside a moving vehicle, that is observing it as it is moving, measured it at 16 meters because of the speed at which that particular vehicle passes. So the observer is not measuring it properly. The person that is in a vehicle is actually the one that will measure the speed at which this particular object moves in its proper state. So that is very importantly for you to know that anytime you're calculating contracted length, it will be somewhat less than what? The proper length. The proper length was 20 meters of this particular rod. The person that is sitting on this rod, is seeing it that it is 20 meters, but the person that is actually standing afar off, watching a rod that is moving, measure it at what? 16 meters. Now, let us answer the fifth question while we continue. Although that in a motor, the induced EMF, that's the electromotive force, that opposes the supply voltage is the dash. A says back electromotive force, B says peak electromotive force, and C says motional electromotive force, and D says eddy electromotive force. What do you think is the answer? Now, let me quickly point something to you. A motor uses electricity to move. And for it to move, there have to be an introduction of electric current. And when electric current is introduced to a particular motor, it causes it to rotate. In the course of that rotation, in the motor, there's actually going to be a little voltage that will be produced. And the voltage that is produced in that particular motor will act against the voltage that is introduced to that motor to enhance its movement. All right. So that particular voltage that is produced inside the motor, as of when it starts moving, that particular force or that particular voltage that is produced inside that motor is called the back electromotive force. It's more like acting against the voltage, the electric current that is introduced to that motor to ensure it moves. All right. So it happens that the correct answer to this question is the back electromotive force. So anytime you look at the word opposes the supply of voltage in a motor, think back electromotive force. The peak electromotive force actually talks about the maximum value of an electromotive force. The motional EMF is simply the EMF that is produced when a conductor comes in contact with a magnetic field. Right? Eddy EMF is simply, these are circular electromotive force that is produced when that is produced inside a bulk conductor. We'll put it like that, right? That's just what the eddy EMF is all about. So the back EMF is the correct answer when you think opposition to what the supply of voltage in a motor. Go to the next. All right, the question says that, question 6 says, when a dielectric is inserted between the plates of a capacitor, its capacitance, A says decreases, B says stay the same, C says increases, and D says becomes 0. What do you think is the right answer? All right, it happens that we need to first understand the concept of what a dielectric is. All right, a dielectric is more like an insulating material that is placed between two plates, all right, in a capacitor. All right, it's placed between two plates or two capacitor plates. A dielectric is what? Is an insulating material that is placed between what? Two capacitor plates. Now, that insulator, insulator is simply a material that current cannot flow through them easily, like glass, like plastics, and all that. Now, the aim of a dielectric particularly is to ensure more storage of voltage, all right, in a particular circuit. Now, for us to understand this principle, first of all, what is a capacitor? Capacitor is simply what is used in storing what? Electrical charges. And the capacitance here tells you how much of charge that can be stored at a given potential difference, all right, of a given voltage. Now, for a normal capacitance, for you to calculate a capacitance, normally capacitance is given as a charge all over the potential difference, all right? But for a parallel plate, please have to take cognizance of this. If you're dealing with a parallel plate, the capacitance is given as the permittivity of the particular material medium that is used, all right, between those two plates, times the area all over the distance between those two plates, for two plates. But then if you now introduce a dielectric, the capacitance will be calculated as K, the permittivity of the space, all over times A, all over the distance between those two plates. Now let us analyze this. This is for you to find a normal capacitance, the given charge all over the potential difference. If it is between two plates, if it's between two capacitor plates, if you're dealing with two capacitor plates, this is how you find the capacitance, right? But if you're now introducing a dielectric, if you're introducing a dielectric, then you have to introduce what they call the dielectric constant. And this dielectric constant is always greater than 1. Now notice, if you introduce a dielectric, what will happen to the capacitance is that it's going to increase. You notice their relationship, they are directly what? Proportional. So addition of a dielectric inserted between two plates of capacitor will actually lead to what? Increase of that capacitance. The capacitance will increase. It will not become 0. It will not stay the same. Decreases, reverse of what it does. So you have to just take cognizance of that. These formulas are very important for you to calculate capacitance, normal capacitance, charge all over what? The potential difference. If it is between two plate capacitors, all right, two capacitor plates, this is how you find the capacitance, the permittivity of that material all over the area of the material times what? The distance between the two material medium. But if it's in a dielectric, there is actually what? The dielectric constant and the permittivity of the material medium or the insulating material medium that is used times the area all over what the distance between those material medium. So the correct option is option A. Next question. I'll need to make a space here so that I'll be able to calculate the next question that follows suit. Next question says that a charge of 5 times 10 raised to the power of minus 3 coulomb moves at 200 meters per second perpendicular to a 0.4 Tesla field. The force on it is, the options A says 0.04 Newton, B says 0.4 Newton, C says 4 Newton, and this is 0.8 Newton. Now, you need to understand the keyword in this particular question. There are different forces. There's force on a current carrying wire. There's force in a solenoid. There's force on a moving charge. All right? There's even force between two plates. All right? Now, one thing you need to understand is that this particular question is coming out from force on a moving charge. And the force on the moving charge, F, is giving us the charge times the velocity times the magnetic field times the angle sine theta. Now, what you need to understand is that there's, from what we have here right now, we have our velocity as 200 meters per second. And we have the charge size is giving us 5 times 10 to the power of minus 3 coulomb. And then let's say perpendicular to 0.4 of the Tesla, that is the magnetic field strength, 0.4 Tesla. We are looking for the force. Now, what you need to know is that what will now be our angle? What should guide you in questions of this manner? If the charge moves at 200 meters per second perpendicular, when it moves in a perpendicular manner, it means that the force is maximum. That's to say that the angle is at sine 90. And sine 90 is equals to 1. But if it is parallel, it means it's sine 0 degree, and sine 0 degree is 0 degree, meaning there is no force actually acting on this. So in a CBT question, if you see that the given charge moves parallel to the magnetic field, just know that the answer is 0. There is actually no force in that regard. But here we can calculate it because it is perpendicular towards the magnetic field. So take cognizance of that very importantly. Sometimes in a CBT question, you might be asked that force on a moving charge is maximum when the given angle is dashed. Sometimes you can see 90, 45, 60, 30 as the case may be. Remember that force on a moving charge is maximum when our given angle is at 90. And when our given angle is at 90, it's the same as saying that it moves in a perpendicular manner. So take cognizance of that. So I'm going to calculate this question right now. So our force is giving us the charge of 5 times 10 to the power of negative 3 times our velocity of 200 times yes, our magnetic field strength is 0 times 0.4. So we all know that sine 90 is the same as 1. So if we multiply with sine 90, it's more like you say multiply with 1. So it's still not very significant in terms of multiplication. So force is giving us, I'm going to actually punch my calculator and then get the final answer. So 5 times 10 raised to the power of minus 3 times 200 times 0.4. It happens that our final answer is 0.4 Newton. So that's actually the force that will acting on this particular magnetic field if the charge moves at this particular velocity. So our answer is option B. The next question says that of alpha, beta, and gamma radiation, the strongly ionizing is, A says beta, B says gamma, C says they are all equal, and D says alpha. Now, it's very important for you to know key things as regards the alpha particle, the beta particle, and the gamma particle. Let's start with the ionization ability. In ionization hierarchy, the most ionizing is the alpha particle, followed by the beta particle, and then lastly by the gamma particle or the gamma ray. That is in terms of ionization ability. So it happens that the correct answer to this question is the alpha. Now, if you are asked in terms of penetration, as in which one has the highest penetration, what I wrote there is reverse. In terms of highest penetration, you start with the gamma, then to the beta, then to the alpha. So it happens that the alpha particle has the lowest penetrating ability, but it has the highest ionization ability. Now, in terms of its charge, if you're talking, if you asked in terms of its charge, the alpha particle is positively charged, having a +2 charge. The beta particle is negative charge, having a -1 charge, and then the gamma ray is neutral. All right, very important for you to know that. Okay, so this is the correct option in that regard. All right, number 9 question says that a photon has a wavelength of 3 times 10 raised to the power of -7 meter. Its frequency is, A says 1 times 10 raised to the power of 15 hertz, B says 9 times 10 raised to the power of 1 hertz, C says 3 times 10 raised to the power of 8 hertz, and D says 1 times 10 raised to the power of -15 hertz. Now we need to know that there's a formula that connects our frequency and our wavelength, and that formula is the speed of light, c, is equal to our frequency times our wavelength. It happens that we are asked to find the frequency of this particular photon, right? So the wavelength, sorry, we are looking for the frequency. I'm going to make the frequency the subject of the formula. So the frequency will be given as the speed of light all over the wavelength. So the speed of light is 3 times 10 raised to the power of 8 all over. Our given wavelength is 3 times 10 raised to the power of -7. In terms of division, these 3 can cancel these 3. Remember the laws? These 3 can cancel these 3. We can have it to be that this is 10 raised to the power of 7, or let's write it as 1 times 10 raised to the power of -7. And if this is 10 to the power of -7, we can say it is 1 times, this is 10. According to the law of indices, this is 8. If it's division, it is minus. And this is also another minus part. So what we have now is that our frequency will be 1 times, now this is 10. Now minus times minus will become plus. This will become 8 plus 7. So it happens that our given frequency is 1 times 10 raised to the power of what? 15 hertz. So from our given solution, it happens that option A is the correct answer. Let's go to question 10. The potential difference across a component is the work done per unit charge measured in. A says ampere, B says ohm, C says volt, and D says watt. This is a very simple question, and I believe you've gotten it right even before I initially answer. Ampere is the measurement unit for current. Watt is what you use, the measurement or the SI unit for power. Ohms is the SI unit for resistance. It happens that what the SI unit for potential difference across a component in terms of the work done per unit charge is given as what? The volt. So option C is the correct answer. All right, so we have a question here that says, question 11 says 2 charges plus 2 microcoulomb and plus 8 microcoulomb are 3 meters apart. The force between them is, now we're told to take the constant here to be 9, electrostatic constant to be 9 times 10 raised to the power of 9 Newton meter square per coulomb square. So we're going to solve that first. So the formula for finding this is simply force is given as the electrostatic constant times the first charge times the second charge all over the distance between them in its squared. Now, before we solve this question, We have the first charge to be 2 microcoulomb, the second charge to be 8 microcoulomb. We have our radius here, or the distance between them, as 3, and we have our constant k. We are to look for the force. Before we do that, we have to convert this microcoulomb to what? Coulomb, right? Because charge is measured in coulomb. So to convert that, the simple thing you're going to do is that to convert from microcoulomb to coulomb, you simply do the given coulomb you're given multiplied by 10 raised to the power of -6. So it's going to be for plus 2 microcoulomb, it will be equals to 2 times 10 raised to the power of -6 in its coulomb. For plus 8 microcoulomb, it will be 2 times 10 raised to the power of -6 in its coulomb. Sorry, what's this 2 is actually 8. 8 times 10 raised to the power of -6 coulomb. So we're going to solve this right now and say force is equals to the constant you are given, which is what? 9 times 10. So this is 9 times 10 raised to the power of 9 times the first charge is 2 times 10 raised to the power of -6 times the second charge is 8 times 10 raised to the power of -6 all over. Our given distance is 3 in its squared. So we're going to actually multiply this right now. 9 times 10 raised to the power of 9 times 2 times 10 raised to the power of -6 times 8 times 10 raised to the power of -6, all divided by 3 raised to the power 2. Our final answer is 0.0116 Newton. If we put all that, so it happened that the correct answer to this question is option D. Next question says, so what this means is that there's actually a repulsive force between these two charges. Why is the force repulsive? Because the two charges are having what? The same charge. They are both positively charged, and we know that like terms repel, but unlike terms attract. So there's a repulsive force of 0.016 Newton between these two charges that have the same value there. Okay, so let's look at this right now. The next question says that a nucleus has a mass defect of 0.05 atomic mass units. They say its binding energy in mass electron volt is, A says 933.5 mass electron volts, B says 46.6 mass electron volt, and C says 9.3 mass electron volt, and D says 0.05 mass electron volt. I need to understand the principle of binding energy, all right? The word binding energy, before I talk about what binding energy is, we know that in the nucleus of an atom, there are two major constituents. It's the neutron and the proton. That is actually in the nucleus of an atom. Now, if we are to separately add the mass of the neutron and the mass of the electron together to form the nucleus, the sum total of the mass of the neutron and the proton added together to make up the nucleus of that atom will be larger compared to the actual mass of that particular particle. That particular difference is what we refer to as the mass defect. And so they say that this particular particle, upon trying to bring the neutron and the proton in their individual mass together, there was actually a mass defect, a difference in the masses of the two proton and neutron compared to the actual mass of that particular particle. They say it has a mass defect of 0.05. And this binding energy here particularly will not help us. Binding energy is actually the energy that is required to separate each constituent in a nucleus, all right, to stand on its own. When you want to remove the proton from the neutron, the energy that aids you to do that is what we refer to as what? The binding energy. Now, for you to be able to calculate the binding energy of any given particle, let me make space here. For you to be able to calculate the binding energy, the binding energy is equals to the mass defect times 931.5. Now, why is 931.5 there? You need to know that one atomic mass unit is equals to 931.5 mass electron volt. It's constant. So for example, the number of mass defects you're given, for you to get the binding energy, you simply multiply that given mass defects times the 931.5 in terms of its mass electron volt, because one atomic mass unit is equivalent to 931.5 mass electron volts. So it's very, very simple. So it happens that the binding energy, BE, in short form, is giving us the mass defect of 0.05 times 931.5. And if I punch that in my calculator, 0.05 times 931.5, the answer I've gotten is 46.6 mass electron volts. So you notice that the correct answer to this question is option B. If you're asked in a CBT that one atomic mass unit of a particle is equivalent to dash in terms of its mass electron volt, just know that it's 931.5 mass electron volt. So this is not up to 1. 0.0 is not up to 1. That's why you see that the mass electron volt is reduced 46.6, because 1 of the atomic mass unit is actually 931. But if it's just 0.0, which is less than 1, it's going to be smaller. So that's why it's 46.6 mass electron volts. Next question says that Faraday's law states that the induced electromotive force is proportional to the dash. A says the current, A says the rate of change of magnetic flux, B says magnetic flux, C says resistance, and D says what? Current. For there to be an induced electromotive force, there must be what? A change in the magnetic flux. It is the change in the magnetic flux that leads to what? An induced electromotive force. All right? So that's just a simple thing. If you're asked any question that has to do with Faraday's law, the induced electromotive force is just proportional to the rate of change of magnetic flux. That is just the correct answer. All these other options are not actually in alignment with Faraday's law. All right, another thing you need to know that is very important. Remember, we said that for an induced electromotive force to be produced, there have to be a rate of change of what? The magnetic what? Flux. Now, for us to be able to change the magnetic flux, there are certain things we need to change that will directly lead to a change in the magnetic flux. We can actually change the angle, or we change the area, or we change the magnetic field strength. Either of these, when it's changed, can actually what? Lead to what? The rate of change of the magnetic flux. Remember Faraday's law. Faraday's law, for the sake of learning, Faraday's law is given as negative of n in bracket the change of the magnetic flux. Let me use my duster. The change in the magnetic flux all over the change in time. So, very important. This n means the number of turns. This is the change in magnetic flux. Sometimes I can be given a question where there's a difference in the magnetic flux from the first to the second. That's why it's written as change in magnetic flux. And change in time can also be given a different time duration. All right. This negative sign here is Lenz's law. All right. And Lenz's law states that the induced electromotive force opposes the change that is producing it. So when you see this negative, remember Lenz's law, because sometimes you can make a test and say the negative sign in Faraday's law is what? You should know that it's Lenz's law. All right. So that's very, very important for you to know. We'll go to the next question that says that in special relativity, as the speed of an object increases, its relativistic mass dash, A says decreases, B says stays constant, C says increases, and D says becomes 0. Now, what you need to know is that the relativistic mass m is related to the Lorentz factor times the mass at rest. The relativistic mass, right, is equal to what? The Lorentz factor times what? The mass at rest. That means that whatever happens in special relativity as the speed of an object increases. Now, remember in Lorentz factor, one of the factors that can actually enhance, way to calculate for Lorentz factor is actually the speed of that particular object, right? So if you increase the speed of the object, you are increasing in special relativity. As the speed of object increases, you are doing same to what the relativistic mass, because the relationship between the relativistic mass and the Lorentz factor is directly what proportional. So whatever happens to the relativistic mass, that's what happens to what the speed of the object. While the speed of the object increases, the relativistic mass also what increases. Very importantly, this is opposite what that implies. The next question says that an electromagnetic wave has a period of 2 times 10 to the power of minus 5 seconds. We are asked to look for its frequency. A says 2 times 10 to the power of minus 15 hertz. B says 5 times 10 to the power of 15 hertz. C says 5 times 10 to the power of 15 hertz. And D says 2 times 10 to the power of 15 hertz. For us to be able to calculate this, we know that the relationship that exists between frequency and period is an inverse relationship. So our given frequency is going to be 1 all over whatever our period is, right? So this is going to be 1 all over. Our period is 2 times 10 raised to the power of negative 15. And if we punch that in my calculator, and okay, 1 all over 2 times 10 raised to the power of minus 15. It happens that we got 5 times 10 raised to the power of 14 hertz. This happens that option B is the correct answer. The frequency will be 5 times 10 to the power of 14 if the period is 2 times 10 to the power of minus 15. Go to the next. All right, Gauss law relates the electric flux through a closed surface to the A says field strength only, B says resistance, C says current, D says enclosed charge. You all know that current is simply the amount of charge that is flowing through a particular circuit. Resistance has to do with electrical circuits. Resistance is not it. And if we say field strength only, Gauss law does not just measure field strength only, it talks about the total flux. So if we are to define Gauss law in terms of what it relates, Gauss law actually relates the total flux, right, through a closed surface to the net electric charge enclosed inside that surface. All right, that's what Gauss law relates. So in terms of formula, Gauss law is more like Gauss law is given as this is the charge enclosed all over. This is what we call the permittivity of free space. So anything that has to do with what Gauss law relates, the correct answer is through the surface, through a surface, through a closed surface to the what? Is to the enclosed charge. Because according to the formula, it's Gauss law in terms of the total electric flux, actually related to what? The enclosed charge that is inside that particular medium. All right, so that's the correct answer. All right, we're given a questionnaire that says a charge that enters a uniform magnetic field perpendicular moves in A says circle, B says straight line, D says parabola, and D says spiral outward. First, let us write out what it means for a particular charge, the force that acts on a charge that moves. The force that acts on a charge that moves is given as the charge times the velocity times what? The magnetic field. Now, anytime a force is actually directed towards velocity, it actually changes that particular medium continuously in the direction of motion. And if it does that, it means we're going to say that that particular force is referred to as what? A centripetal force. When it's actually a continuous change in the direction of the particular object. So there's actually a relationship between the force on a moving charge with a centripetal force. All right, and centripetal force is given as mass times velocity squared all over the radius. Now, this is force that is equal to this and force that is equal to this. So we can relate this force on a charge with force that acts towards velocity. All right. Now, if that's how we're going to relate it, we're going to actually make this R radius the subject of the formula. All right. And doing that, we're going to have it that R is equals to first. I'm going to cross multiply. So R is QVB equals to MV squared. So R alone is going to be MV squared all over QVB. And it happens that you can reduce the velocity and say that our R, which is the radius, is equals to the mass and the velocity all over the charge times the magnetic field. So this actually means it's going to be in a circular movement, right? It's going to be in a circular movement. So the correct answer here is that it's a circle, and not it's going to keep it in that circle as it's moving. It's not going to spiral outward, and it's not going to be in a straight line because it's not force. It's not it's not a horizontal movement. It's a circular movement, all right? So the straight line equation is not going to work here, and that with parabola. So this is what will relate this particular equation. So anytime you hear that a charge enters a uniform magnetic field, think circular. Very important. Circular movement. Okay. And another thing that you need to know that could be a likely CBT test or question is that under what condition does the radius increase? The radius increase when you increase mass or the velocity, but the radius decreases when you increase the charge or the magnetic field intensity. So you need to understand that what the radius is actually inverse, right, to the charge and the magnetic field. So if you increase this, this will reduce. If you decrease this, this will increase. It's an inverse relationship. Whatever happens to the radius is what will happen to the mass and the velocity. So if you increase mass and velocity, you're indirectly increasing what? The radius. But if you increase the charge and the magnetic field intensity, you're going to reduce the radius. That's just the relationship that exists there. All right, number 18 says a radioactive nuclide has a decay constant of 0.0347 per second. Its half-life is about, A says 0.05 seconds, B says 2 seconds, C says 20 seconds, and this is 200 seconds. Now, it's very important for you to know that there's a formula that connects the half-life to the decay constant. Anytime you are given the decay constant and I to look for the half-life, the simple thing is you just do half-life is equal to 0.693 is constant all over what? The decay constant. So if we impute that, we're going to have our decay constant 0.0347. So 0.693 all over 0.0347. All right, so from a calculator, half-life of half-life of 0.0693 divided by 0.0347, it will be equal to 20 seconds. So it happens that the correct answer to this question is option C. That is the half-life of this particular particle. Next question says the scientist who proposed fixed circular orbits of definite energy for hydrogen atom was, A says Dalton, B says Thomson, C says Chadwick, and D says Bohr. Now, it's very important for us to understand these scientists listed there and what were their contributions to scientific evolution. Dalton here is regarded as one of the earliest speaker in respect to atomic theories or atoms, all right, in terms of the formation of atoms. Thomson talks about the electron. He discovered electron, and also he's attributed to what they refer to as the plumb pudding. The plumb pudding model. So when you hear electron and plumb pudding models, think J.J. Thomson. Chadwick is the person that discovered neutron. All right. And so it happens that the person that spoke about energy given in a definite proportion, right? In a fixed circular orbit, all right, is actually Neil Bohr. So the correct answer to this question is Neil Bohr. Very importantly for you to know. So if you hear neutron, remember Chadwick. If we talk about electron and plum pudding models, remember Thomson. They talk about the earliest speaker of atom theory or atomic theory is Dalton. Question 20 says, let me make space as we, because we need to solve that particular question. Question 20 says that two resistors of 5 ohms and 5 ohms are connected in series. The total resistance is A says 2.5 ohm, B says 10 ohm, C says 25 ohm, and D says 1 ohm. Now, for you to understand this question, anytime resistors are connected in series, so let me quickly write something down. When resistors in series, for you to get the total resistance is simply resistance total is equals to the first resistance plus the second plus the third and so forth and so forth. But in this case, we have two resistance. All right, so anytime resistance is connected in series, the total is just going to be the sum, the algebraic sum of their individual resistors. So it's simply 5 plus 5, which will give us 10 ohms. So option B is the correct answer. But what if this was actually connected in parallel? If you notice, we have the same ohm, 5 and 5. So when you have the same ohms and the resistors is connected in parallel, not in series as it is in this question. So let's say resistors of the same resistance connected in parallel, you simply do the resistance total as resistance all over. You just pick one of them all over 2. That is to say, if this resistor was actually connected in parallel, I'm just simply going to say it's going to be 5 divided by 2. It's going to give us 2.5. So if I'm going to give us 2.5 ohm. If it was connected in parallel, this A would have been the correct answer. You see, some of these things are the distractors they put in exams, and if you're not very cognizant with it, you might actually miss out, right? If this was resistors that are connected that of the same resistance, like 5 ohm and 5 ohms in parallel, all right, you're just going to simply do one of them, one of the resistance, you're going to divide it by 2, and you get the resistance total as that. Now, if they are not of the same ohms, sorry, of the same resistance, and let me say we have 3 and 4 also, we're just simply going to do that the total resistance is going to be 1 all over. The resistance is going to be 1 all over resistance 1 plus 1 all over resistance 2 and so forth, and you get the total resistance. All right, question 21 says that charge is quantized, meaning it exists only in whole number multiples of A says the elementary charge, B says the permittivity of free space, D says the Coulomb, and D says just K. Now, anytime anything has to do with quantization of charges, it's actually a whole number multiples of what the elementary charge. Now, when you're talking about the quantity of charge is equals to the integer of the elementary charge. This is the formula that relates this particular equation. All right. So when we talk about charge, which is Q, is quantized, meaning it exists only in what whole number multiple. This n is an integer, whole number multiple of what the elementary charge, and where this elementary charge E is actually a constant of 1.6 times 10 to the power of minus 19 Coulomb. Very important for you to know. So the correct option to this question is option A. The next question says that a nucleus with a higher binding energy per nucleon is A, less stable, B, radioactive always, C, C, more stable. This is more stable rather, please. more stable, and E says electrically charged. Now you need to understand the concept. Prior to this time, we've talked about the binding energy. I would say the binding energy is more like the energy that is required to actually separate individual constituents of a nucleus, all right, to different parts. Now, we'll talk about a nucleus. A nucleus is made up of the neutron and the proton. So the energy you need to separate them to the individual constituents is referred to as what the binding energy. So now they ask us a question that if a nucleus with a higher binding energy, remember, this is energy required to break this nucleon. So they say if it has a higher binding energy per nucleon, now the nucleus, what is the state of the nucleus? Is it less stable? Is it reductive always, or is it more stable, or is it electrically charged? Now it happens that when a particular nucleus requires a higher binding energy to break, it means that it is very stable or is actually tightly held together. So it will require more binding energy to break than a nucleus that is not actually tightly held. Now, assuming we have, let me say, nucleus A, and then we have nucleus B on this side. Now, nucleus A, for you to get, let me assume that it has a total energy of, let's say, 80 mass electron volts, and the number of nucleons is actually 10. And let me say another nucleus B has a total energy of, let's say, 60 mass electron volt, and it also has nucleon of 10. For us to get the binding energy, we're going to simply do this total charge all over the nucleon. So it's more like 80 divided by 10. So this is going to give us 8 mass electron volts here in this particular first nucleus. The second one, for us to get the binding energy, we're going to do something like 60 divided by 10, and this is 6 mass electron volts. So what does that tell us? This particular nucleus that has 6 mass electron volt, it means it is not as tightly held together as the nucleus A that has a binding energy of 8 mass electron volt. That's to say, if we are actually to separate the proton and the neutron to their individual constituents, we will need more binding energy to break this than we will need to break this. So in summary, the higher the binding energy, the more stable the nucleus is, all right? The more tightly held together it is. So it happens that the correct answer is option C. Understand that principle very importantly. Less stable is actually opposite of it. It will only be less stable if there's actually, if the nucleus does not have a higher binding energy, let's say less binding energy, then of course to be less stable as well. Other options, reductive always is a CBT trap for that. So the correct answer is option C. Question 23 says a solenoid of 500 tons per meter carries 4 ampere. Now the field inside is, A says 1.26 times 10 to the power of minus 6 Tesla. B says 500 Tesla. C says 2000 Tesla. And D says 2.51 times 10 raised to the power of minus 3 Tesla. Now, you need to understand the principle of a solenoid. A solenoid is a long coil containing many closely wound turns of wire, right? Very importantly. And then for you to be able to calculate the solenoid in a magnetic field. Now, before we even calculate this, it's very important for you to know how to differentiate these particular formulas I'm about to write out. We have magnetic field in a moving charge. Magnetic force, rather, of a moving charge. So when there's force on a moving charge in a magnetic field, we say force is equal to QVB. When we have force on a current carrying conductor, all in a magnetic field is given as the magnetic field times the current times the length and sine theta. And then we have magnetic field in a solenoid. That is what we're about to write now. So magnetic field is given as the permeability of free space times the number of turns times the current. It's very important for you to know that. Now, you have to take cognizance of this because it's very, very important. All right. Now, from this particular question, this permeability of free space has a constant, and that constant is permeability of free space is 4 pi times 10 to the power of minus 7. All right. Then we have the number of turns. Our number of turns n is 500 turns per meter. 500 turns per meter. And then we have our current was given to us as 4 ampere. Now, for us to be able to solve that, we just input it into this particular formula and we solve. So, magnetic field in a solenoid is, now remember 4 pi is 3.142. So we can just keep writing this times 10 to the power of minus 7 times 500 times 4. All right. So that's what we have there. So magnetic field is 4 times 3.142 times 10 to the power of minus 7 times 500 times 4. So if we multiply all of that together, we should have one particular value of the magnetic field inside this particular solenoid. All right. So we have 4 times 3.142 times 10 raised to the power of minus 7 times 500 times 4. So it happens that our answer is 2.51 times 10 raised to the power of minus 3 Tesla. That is the magnetic field in this particular solenoid. And it happens that the correct answer is option D. Option D is the correct answer for this. Then question 24 says, the principle of equivalence relates a gravitational field to, A says an electric field, B says an accelerating frame, C says a magnetic field, and D says a vacuum. What do you think the answer is or will be? Now, the keyword here is equivalence. Equivalence, equality. Whatever gravity is doing, which of this option is actually doing that in opposite to gravity? That's what they are asking us in essence, all right? Now, we all know that a vacuum is simply an empty space, so it does not really equate to equivalence in respect to what gravity, in respect to a gravitational field. An electric field is just actually done in terms of electric charges, all right? It's in electric charges that electric field is actually experienced. Magnetic field is actually experienced within what? Magnetic charges, all right, or current. It happens that the correct answer is an accelerating frame. Now, let me paint a picture to you. Assuming an observer, when we say a frame is more like the coordinate system where the observer is standing to measure the direction of motion, all right? Assuming someone is actually in a lifter, all right, and the person is in that lifter, and the lifter is actually carrying the person upward, and the person cannot see outwardly what is happening, but the person understands that he's actually going up. Now, as the person is actually going up, there's actually a force, even as he is inside that particular lifter, there's a force that is keeping him tied to the base, the floor of that lifter, and that force is gravitational force. So as that particular lifter is accelerating upward, there's actually a gravitational force that is also acting upon that person that is in that elevator, bringing the person down, or actually keeping the person stuck towards the base of that particular elevator. So you notice that as the person is being lifted up, right, by that particular elevator or lifter, the person is actually on the base, standing on the floor of that particular elevator. So as the person is accelerating, gravity is also keeping the person center of that particular elevator. So the principle of equivalence applies to what? That the principle of equivalence relates a gravitational field to what? An accelerating frame. That's the correct answer to that question. Question 25 says that a conductor of length 0.2 meter moves at 5 meter per second perpendicular to a 0.6 Tesla field. The motional electromotive force is A says 0.06 volts, B says 6 volts, C says 0.6 volts, and D says 0.024 volts. Now, this is a question that we will need to wipe off this board to be able to solve. So, in respect to the motional EMF moving in a perpendicular manner towards the magnetic field, it is given as the electromotive force, all right? That motional electromotive force is equals to the magnetic field times the length times the velocity of that particular movement. So you need to know these formulas. They are very important, okay? Because this actually conductor of length that moves what perpendicular to what is 0.6 Tesla field. So it's magnetic field strength. And so the electromotive force is simply um, the magnetic field strength times the length times what? The velocity. And that's how we're going to get the motional electromotive force. So looking at this question, we have a magnetic field strength of 0.6 Tesla. We're given the length as 0.2 meter. And then, the length, yes, the length as 0.2 meter. And then our velocity was given as 5 meter per second. So we can apply that in solving. So the electromotive motional electromotive force is going to be 0.6 times the length of 0.2 times the velocity of 5 meter per second. And if we punch that on the calculator, 0.6 times 0.2 times 5. It happens that the correct answer to this question is 0.6 volts. So option C is the correct answer. All right, question 26 says, two 6 microfarad capacitor are connected in series. The total capacitance is, A says 3 microfarad, B says 1.5 microfarad, C says 6 microfarad, and D says 12 microfarad. Now, for us to solve this question, you need to understand there's a key difference between a capacitor and a resistor. And there's also a big difference between how they are connected, right? Now, if a capacitor is connected in series, remember they are identical. Now, let me write this down. Identical connections. Let me quickly make. So if we have two identical, let's say this is a capacitor. We have two, because you need to know this difference is very important. Identical resistors. Let me not even go there. Now, for you to be able to, okay, now two identical resistors and two identical capacitors. If it is for two identical resistors, that is actually connected in series, two identical capacitors, let me write the word in series, two identical resistors in what? Parallel. When it is two identical capacitors in series, you simply do the total capacitor is going to be the capacitance all over 2. And if it is two identical resistors in parallel, you simply do the resistor total is equals to what? Resistor all over 2. It's the same. But then you need to understand the principles. Yes, the both of them are identical, but notice that when capacitors are connected in series and there are two identical resistors, or there are two identical capacitors, you can solve the total capacitance this way. And if the two resistors are actually in parallel, they are connected in parallel, is the same way. Same way in solving it, but know the condition that actually leads you to use that. So it happens that this particular question says 2 microfarad capacitors are connected in series. So the two or the total capacitance is going to be equal to what? this divided by that. So this is 6. So we're going to simply say it is what? 6 all over 2, and it will be 3 microfarad. So the correct option to this question is option A. Very important. With what we've done here, you should understand that if they are not identical, and let's assume they are not identical, and then you're dealing with capacitor total. Let's say you're giving 2 capacitors, right? If you're giving microfarad or whatever, and you are giving that capacitors in, okay, let me start with resistors before we go to capacitors. For resistors, if resistors are connected in series, and let me say they are different, they are dissimilar. Let's assume we have 2 ohms and 3 ohms. If they are connected in series, you simply what? Add this plus this. That's how you get the resistance or the resistor total, right? The total resistance. That's how you do it. But in terms of capacitor, if they are connected in series, reverse is the case. You're going to do the inverse of them. You're going to say it's 1 all over. Remember, in this place, if it is what? If the connection is what? It's in series. For resistor, if it is in series, you're going to say resistor total is going to be 1. Sorry, it's going to be the R1 plus what? The R2. If this is in series and they're dissimilar, opposite of it, you're just going to 1 all over C1 plus 1 all over C2. Remember, dissimilar. Let's assume what we have here now is 2 microfarad and 3 microfarad. 2 microfarad and 3 microfarad. In series of dissimilar what? Dissimilar capacitors, dissimilar resistors. If it is in series, you simply add the resistors together. But if it is in series in capacitor, you do opposite of it. Now, if it is in parallel, that's when you do inverse of this in resistor. So if resistor is connected in parallel and the 2 resistors are different, if it is in parallel, resistors in parallel, we're going to do 1 all over the resistor total is equal to 1 all over R1 plus 1 all over what? R2. Resistors in parallel. How about capacitance in parallel? That's when you add up like this. Capacitance in parallel, that's when you do the capacitance total as C1 plus what? C2. So you need to understand something. For dissimilar resistors and capacitors, they are always opposite each other in terms of how you solve them, right? If capacitance is in series, and they have 2 separate capacitors, you're going to do 1 all over this and solve. If resistor is in series, you're just going to sum it up. What you're doing for resistor is opposite for resistor in parallel. So resistors in parallel is now inverse. Capacitor in parallel is now simple what? Algebraic sum of the individual capacitors. So know those principles is very important. But for the 2 identicals, you've seen the difference. 2 identicals, this is the difference. But you have to know the application. This has to be in series and this will be what? In parallel. That's the difference. And then if they're actually in series, but then they are dissimilar, they're no longer identical, they're now in series. All right? It's simply going to solve the total capacitance total as using this formula, and the resistance total using this formula. They are not connected in parallel. This is a capacitance total. Simply add them together. Then for resistance, it's now like the inverse of it in terms of what's the total. I believe you understand that principle. All right, let me take this off. Now we are going to solve the question number 27. The question says a wire carries 10 ampere at 90 degrees to a 0.2 Tesla field over 0.5 meter. The force is, now I remember I told you that there's magnetic field in the solenoid. There's force on the current carrying conductor. There's force on a moving charge. Force on a moving charge is called QVB. which you know already has the charge times the velocity times the magnetic field strength. But now we're dealing with force in a current carrying conductor. And the force in a current carrying conductor is given as F is equal to VIL sine theta. Now, remember the current that is given to us here, that's our I. Let me write out each of what we have now. Our current is given to us as 10 ampere, and our length is given to us as 0.5 meter. And then we have our magnetic field strength as 0.2 Tesla. And then for us to be able to find our sine theta, now sine theta, in some question they will say it is perpendicular. In some question they will give the exact angle. Now, anytime sine theta is regarded to as perpendicular, it means it is sine 90. If they don't give you as an angle like it is here right now, they say perpendicular, just remember it's sine 90, and sine 90 is equals to 1. All right? Very, very important. So sine 90 as given to us in that question is equal to 1. We all know sine 90 is equal to 1. But if they don't give us sine 90, remember, so if they write it as perpendicular, just know that they are talking about sine 90, which is still equal to 1. So we're going to apply this straight up and solve for this particular question. So it happens that the force on this current carrying conductor is going to be our magnetic field of 0.2 times the current of 10 ampere times the length of 0.5 times 1. So if we multiply that all through 0.2 times 10 times 0.5, it happens that we have 1 Newton. So the correct option to this question is option D, which is 1 Newton. All right, question 28 says, when a nucleus emits an alpha particle, its atomic number, that is, A says increases by 2, B says decreases by 2, C says stays the same, and D says increases by 4. Now, what we need to understand is that an alpha particle, you all know, is represented with this, is an helium atom, 4 here and 2 here. That means any particular particle that undergoes alpha particle emission, it's actually going to decrease by 4 in its mass number and decrease by 2 in its atomic number. All right. Take for example, if we have an uranium particle of 238 in its mass number and 92 in its atomic number, it's going to undergo decay, and then if it's as an alpha particle decay, it's going to be reduced to thorium, which is 234 the thorium particle and 90 in its mass number plus. This shows that it is an alpha particle that was involved in this particular emission. So when a nucleus emits an alpha particle, its atomic number will actually, if you notice, that's decreased by 2. And the same thing happens. So the mass number of alpha particle decreases by 4, but the atomic number decreases by what? 2. So it happens that the correct option is option B, to decrease by 2. Question 29 says that light behaves as particles in the A says photoelectric effect, B says interference of light, C says diffraction of light, and D says refraction of light. Now, it is very important for you to understand that there's what we refer to as the wave duality particle of light. All right, I'll talk about the wave particle duality, right? Yeah, the wave particle duality of light. I want to talk about wave particle duality of light. It is presenting light that light can behave as a particle and it can also behave as a wave. Now, the aspect of light that defines its wave behavior is the interference, the diffraction, the refraction. All of those deals with the wave aspect of light. But the part of light that exhibit light behavior as a particle is the photoelectric effect. It's very, very important for you to know that. So light behaves as a particle in the photoelectric effect, but they could also ask you and say which of these is not the wave behavior of light. If you see photoelectric effect as an option and strike it out, these other ones are the wave behavior of what? Of light. Very important. Question 30 says, in a parallel circuit, the total resistance is always, A says larger than the largest branch, B says equal to the sum, C says less than the smallest branch, and D says what? 0. Now, it is very important for you to understand the particular state in which particular circuit is connected. It's connected in parallel. So, take note, this is a resistance. I told you before, if a circuit is connected in parallel, to get the total resistance, what are you going to do? It's simply 1 all over what? The resistance total is equals to 1 all over the resistance of the first plus 1 all over the resistance of the second. Now, it happens that anytime a circuit is connected in parallel, the total resistance will always be less than the smallest branch. That's the correct option. The total resistance will always be less than the smallest branch. How? Let's assume that we are given two resistance. Let's say 3 and let's say 6. Okay, let's put it like this. Let's say resistor 1 was given as 3 ohms and resistor 2 was given as 6 ohms. Right? If we are to find the total resistance of these particular 2 resistors, let's see what will happen. Remember, I said that it's in a parallel circuit that the total resistance is always less than the smallest branch. Now, between these 2 resistors, which of them is the smallest? It is the resistor 1 that is the smallest, which is 3 ohms. So let us look at what the total resistance will give to us. So this is 1 all over, resistance total is 1 all over 3 plus 1 all over 6. So the resistance total is going to be, the LCM of this is 6. 6 divided by 3 is 2. 2 times 1 is 2 plus 6 divided by 6 is 1. 1 times 1 is 1. So it's happened that we have 1 all over the resistance total is equals to 3 all over 6. So if we cross multiply this particular equation, we'll have 3, the resistance total equals to what? 6. And the resistance total is going to be 6 divided by 3. This will give us 2 ohms. See? So the resistance total is 2 ohm and it is smallest than the smallest of the 2 branches. Have you seen? So anytime you are actually calculating the total resistance and the circuit is connected in parallel, have it in mind that the total resistance will always be smaller or will be less compared to what even the smallest of the 2 resistors that you're dealing with. All right, so go to the next question. All right, question 31 says the number of electrons in a charge of 1.6 times 10 to the power of minus 18 coulomb is. These are A says 16, B says 10, C says 1.6, and D says 1. So we're going to actually calculate this number of electrons. All right. Remember that the charge is given as the integer times what? The elementary charge. All right. Now we're given that the electron, a charge of 1.6. That's to say that our charge Q is 1.6 times 10 to the power of minus what? 18. We are asked to find what? The number of electrons. Now, we have our elementary charge also, so we're looking for n, which is what? The number of electrons. And this n is actually an integer. It's not going to be a fractional number. So even this option that has fraction is actually out of place already. So let us look at this right now. That the number of electron is equal to our charge all over our elementary charge. So elementary charge E is constant as 1.6 times 10 to the power of minus 19 coulomb. Now we are given our charge already as this. So our number of charge is going to be this given charge. So our number of electrons is going to be this given charge, which is 1.6 times 10 to the power of minus 18 all over 1.6 times 10 to the power of minus 19. Now 1.6 and 1.6 can cancel out. Our n will be equals to, this is going to be 10 to the power of minus, let's say This is going to be 1 times 10 raised to the power of minus 18 all over 1 times 10 raised to the power of minus 19. Suppose our n is, according to this law, we just write that 10 because 1 divided by 1 is still 1. So 10 is the power of minus 18. According to the law of indices, if you're dividing, it's going to be minus. It's going to be minus 19. All right. N is going to be 10 raised to the power of minus 18. This is minus 18. Minus become plus 19. So it happens that our n is equals to, this is 10 minus 18 plus 19 is 10 raised to the power 1. So the number of electron is 10. It happens that option B is the correct answer. All right. Atoms with the same mass number but different atomic number are: A says isotope, B says isotone, C says nucleon, and D says isobars. What do you think is the answer? Do have to drop it in the comment section. We all know that isotopes are simply elements of the same atom having the same atomic number but different mass number. So this is a keyword. Let me make space here. For isotopes, sameness, same what? Atomic number. And but there's what? A different mass number. Same atomic number. For example, if we have a carbon atom, sorry, I need to change my marker. If we have a carbon atom that is, let me say carbon 12, it has 6 in its atomic number, and let's say another carbon 14 is still 6. So you see, they have the same atomic number but different mass number. So we call this an isotope. This is not the correct answer because they are asking us for same mass number but different atomic number. All right, so that's isotope. For isotones are simply elements that have the same neutrons in them. All right, same neutrons in them. For example, if you're dealing with let's say you're dealing with neon as an atom, all right, and you're dealing with sodium as an ion. Remember that these have 10 electrons in them. When they have the same electrons, all right, you're dealing with what? Isotones. If this charge, this sodium ion is going to lose one particular electron, making it to have 10 electrons, and it will now be the same with what? Neon atom. You see, they have the same number of what? Electrons in them. Okay. Now, for nucleon is simply proton and neutron. That's what makes up nucleon, right? Isobars here is the correct answer. So when you hear same mass number, think isobar. When you hear same atomic number, think isotope. When you hear neutral or the same number of electrons in them, all right, just think what? Isotones. Very, very important for you to know. The next question is: magnetic field lines always form, A says close to, B says open line ending on poles, and C says straight radial lines, and D says a single point. Simple and straight to the point question. Anything has to do with magnetic field lines, it actually moves from the north pole inside the magnet, right? The movement is from the north pole to the south pole. But outside the magnet, it moves from the south towards what? The north. And in each of those alternating movements, it actually forms what we refer to as closed loops. All right? Magnetic field always form closed loop. Now, this is a very often tested CBT question that you need to know. So the correct answer is what? Closed loop, not open lines. They don't have open lines. They don't have straight radial lines as well, and they are not at a single point. Or they move from the north to the south. All right? The next question, therefore, says at everyday speed, then the speed is less than the speed of light. The prediction of special relativity is A says diverge from Newton's, B says become infinite, C says reduce to Newtonian result, and D says are meaningless. Now the word are meaningless is not part of the option, so that's totally struck out. And also the speed cannot be infinite. It cannot be infinite. Even the speed of light is actually measured at 3 times 10 to the power of 8 meter per second. So the option is between diverge from Newton's and reduce to Newtonian result. Now, when the speed of an object is actually too small compared to the speed of light, very less, it's almost like it's zero. All right. In that particular situation, we'll have it that it is reduced to Newtonian what? Result. In a sense that if we are dealing with the contracted length now, if the contracted length is given as this, the square root of 1 minus velocity square all over the speed of light. It happens that in this particular situation, if the velocity is too small, right, and it's almost equal to zero, and if we write it as zero because it's too small compared to the speed of light, it's not really significant, right, to measure with. So we can have it that the contracted length is equals to the proper length. Then we'll have the square root of 1 minus, let's say 0. And then the contracted length is going to be equals to the proper length times the square root of 1 is still 1. And if you let me make space here. If you do this, the contracted length is going to be equal to the proper length. So there is no contraction in that particular. And when there's no contraction, it just reduce to what? Newtonian what? Result. So the correct option, like I just said, is reduced to Newtonian what? Result. So in a CBT question, once you just say that at everyday life, the speed is less than the speed of light, in terms of the prediction of special relativity, the relativistic what? The prediction will always be reduced towards the Newtonian result. Take note of that. Question 35 says the wavelength of light of frequency 5 times 10 raised to the power of 14 hertz is. We all know that the speed of light is related to the frequency by this particular formula, and we are asked to find the wavelength of the light given that particular frequency. So the wavelength is equal to the speed of light all over the frequency, and this is 3 times 10 raised to the power of 8 all over the given speed. Sorry, let's make this right. 3 times 10 raised to the power of 8 all over the given frequency is 5 times 10 raised to the power of what? 14. Let me punch my calculator. And so if we do 3 times 10 raised to the power of 8 divided by 5 times 10 raised to the power of 14, it happens that my wavelength will be equals to 6 times 10 raised to the power of -7 meter. All right, so the correct answer is option D, which is 6 times 10 to the power -7 meter as a wavelength. All right, question 36 says the oscillation in an LC circuit involves energy exchange between the A says 2 resistors, B says capacitor and inductor, and C says battery and switch, D says wires and air. What you need to understand is that if it's an LC circuit, it's very self-explanatory. An LC circuit consists of 2 major things. An L, which is the inductor, and a C, which is the capacitor. There's actually a back and forth movement between these two particular material medium, where if you are to calculate the energy that is stored in this magnetic field, you're going to say energy stored in the magnetic field is going to be given as length times what? Current squared. And if you're to calculate the energy stored in electric field, you're going to say energy stored in electric field is going to be capacitance times what? The potential difference squared. That is very important for you to know, right? So then we are going to go to the next question. So the correct option for this before we go to the next question is what? The capacitor and inductor. So anything out of the LC circuit is actually an exchange of energy between what? The inductor and the capacitor. All right, 37 says an ammeter is connected in a circuit in A says parallel, B says a separate loop, C says series, and D says reverse. Now, in a circuit, ammeter is normally connected in series. What is connected in parallel is the voltmeter in a circuit. All right. So you just need to understand that particular principle. Very important. So it is in series because ammeter normally measures electric current, and for ammeter to be able to measure the current of a component, the current has to pass through the ammeter itself. All right, and that will actually cause what we call the ammeter resistance. Now, if you're dealing with the ammeter resistance, let me take this off. If you're dealing with ammeter resistance, in ammeter resistance, right? It is connected in series, and in terms of the resistance, there's actually a low resistance if it's for ammeter, right? But if it's for a voltmeter, it's connected in parallel, and it's actually going to have what? A high resistance. So I'll need to know even between these two. That's very, very important. Okay. So go to the next question. Question says a source of activity 80 becquerel, as big as becquerel, has a half-life of 4 hours. Its activity after 12 hours is A says 10 becquerel, B says 400 becquerel, C says 200 becquerel, and D says 50 becquerel. Right? Now, let me make space here so that we'll be able to solve this question just above here. All right. This is a question from radioactivity, and it's very important for you to know how to solve this. So anytime you're dealing with activity, there's a formula that connects that. Activity is equals to the initial activity times half of the number of half-life, where the number of half-life in itself, this n, is going to be little t all over the half-life. This actually the time it took for this particular source to decay, which is what? 12 hours. That's activity after 12 hours, right? And then it has a half-life of 4. So for us to get this n, which is the number of half-life, we're going to do 12 divided by what? 4. And if we do that, we're going to get half-life of 3. Okay? So we are told that this source of reactivity, meaning from its initial state, it was 800 becquerel. So we want to know what will be the number of becquerel that it will have after 12 hours, right? We're going to say that the activity is equals to 800, which is the initial becquerel. Now, in bracket of half times this n, we have gotten it as what? 3. So this is 800 times. Now, 1 raised to power 3 is 1. 2 raised to power 3 is 8, because 2 times 2 times 2 to 3 places. So this is equal to 800 all over 8. And if you divide 800 by 8, it will give you 100. The unit of activity is becquerel. So the correct answer is option A, 100 becquerel. Next question says that the maximum kinetic energy of a photon electron when the Planck constant times the frequency is equal to 6 times 10 to the power of minus 19 joule, and the work function is equal to 2 times 10 to the power of minus 19 joule is. These are the options, and I want you to try to pause the video and solve it yourself. So let us go. It happens that the energy of a photon is equals to we're going to solve it in this manner, that the energy of a photon is equals to the work function plus the kinetic energy in its maximum. All right. And this energy of a photon is more like you saying HF is equal to this work function. This is the symbol plus the kinetic energy maximum. All right. So we are asked to find the kinetic energy maximum. Making kinetic energy maximum is subject to the formula. We're going to have it that kinetic energy maximum is equals to, we're going to have this energy of a photon, which is the Planck constant times the frequency, minus the work function. Now, from what we have, we are giving our energy of the photon as 6 times 10 to the power of minus 19 joule, then minus Our work function was given to us as 2 times 10 raised to the power of minus 19 joule. And if we do that, it's the same power. We simply do 6 minus 2, which is what? 3 times 10 raised to the power of what? Minus 19 joule. So it happens that our correct option is option B. The next question says that the next question says that the electrical energy used by an appliance is given by, it says V over I, C says W is equals to PT, and P equals to IRNC, and D is Q is equals to IT. Now, for you to get the electrical energy used by an appliance, you are going to say in essence that power is simply what? The energy transfer per the time taken in transferring that particular what? Energy. So it's more like power is equals to the work all over the time. Now they're talking about the energy, and the energy in this particular situation is synonymous to the work that is done, all right, by that appliance, all right. So now in essence, we're going to say that the given work is going to be the power times the time. So this is actually going to be the formula we use to find the energy used by what? An appliance. And correct answer is option B. Power is equal to IR is not correct. You know, IR, that's current and resistance, actually talking about ohms. This is resistance, which is voltage all over what? The current there. And that is actually the quantity of charge, quantity of electricity, which is equal to what? The current times the time. So that's not the option. All right, we've come to the end of this particular series of physics. Know it that we are going to still solve the part 2 of this physics and part 3 and part 4 in preparation for your exam. Any part of the world you're preparing for your CBT based physics exam, this will guide you a whole lot. And please, very importantly, do not forget to always visit our channel, the Insight Tutorial channel, for all tutorial updates. And as we end this particular class, I want you not to forget to like, comment, share, subscribe, and follow our channels for all tutorial updates. Thank you very much. May I to talk without